Good morning. These are our AP Calc AB notes for 6-1, slope fields and Euler's method. So we're actually not even going to look at Euler's method though. So just try to get everything adjusted here. So first we're talking about general and particular solutions of a differential equation. So first of all, we were talking about a differential equation. A differential equation can have a derivative in it. It can have our original y in it. So our differential equation could be something like 4y double prime minus y prime plus 3y equals 0. It could be something crazy looking like that. So general and particular solutions are all going to satisfy this. So if you plug in y, you plug in the derivative, you plug in the second derivative, it's going to work. It's going to satisfy that. So general solutions, though, are going to have a c in them. So some kind of constant, and there could be more than one constant. So they're going to have constants. But a particular solution, you are going to use the initial conditions to find that value of c. So when we talk about solutions, it's going to be solutions that when you plug in your y or your first or second derivative, whatever derivative that they call for in that differential equation, all of them are going to satisfy it. And there could be a lot of different values of c that will still satisfy that. But a particular solution, you're going to have specific initial conditions, and you're going to have a value for c. So we're talking about differential equations now. And differential equations are going to contain one or more derivative in them. So when I am working on example 1, all I'm trying to do is figure out if the function is a solution of the differential equation. So when I look at this differential equation here, it has our second derivative minus our original function, and it should equal 0. So I'm going to have to go through and I'm going to have to find my second derivative, and then I'm basically just doing an answer check. A lot of your homework is like this. I think problem 13 is where they are like this. So if you get stuck, that might be a good place to start. So y is sine x. That means my derivative is going to be cosine x. And then when I take my second derivative cosine is going to be a negative sign. So I'm kind of back to where I started with, but I've got a negative now instead of a positive. So now that I've got my second derivative, I want to check to see if y double prime minus y is equal to 0. So in order to check that, I'm going to substitute my second derivative minus my original function. And I'm checking to see, does it equal 0? Well, that would be negative 2 sine x equals 0, which is not true. And so I would say it is not a solution. All right, second one, I am looking at taking my first and second derivative again. So I know the way this works, my first derivative, this is the 4 is just a constant. So I'm going to write that down. My derivative of e to the negative x is going to be e to the negative x times derivative of negative x, so times the negative 1. So I'm going to put a minus out in front. When I take my second derivative, negative 4 is my constant, and then I'd write down e to the negative x, but my derivative of negative x would be a negative 1. So this is going to change back to positive. So I'm doing like constant in front just stays, derivative of e is still that thing, but then you have to do chain rule for the exponent. So now I'm going to check to see if it works in that differential equation. So let's go ahead and check it out. So second derivative, so 4e to the negative x minus original function is 4e to the negative x. Does that equal 0? Yes, so it is a solution. So a lot of your homework is going to be yes solution, no not a solution. So C looks really similar to B, except this is a particular solution. I don't have any constants in it. And this is a general solution because I do have a constant. So in order to check this one, I'm going to do the same thing. I'm going to find my first derivative. Well, this is just going to be c e to the x. And my second derivative, same thing. E is its own derivative. And the constants just multiplied in front. There's nothing in that exponent that I need to do chain rule on. The derivative of x is just going to be a 1. So now I'm going to check again. So c e to the x minus c e to the x equals 0. So it looks like It is a solution for any value of C. So yes, it's a solution, but I could put anything in for C and it'll still work. So I'm going to add that for any value of C. So now we're looking at solution curves. This is a little picture from your book. And the solution curves, each one represents a particular solution. So a general solution itself is going to represent a family of curves. And then each of these curves is a different value of C. So I'm not really sure how we'll write that out. General solution represents family of curves. Let's see. Each one is a, is a certain value of C. Now, in order to to find a particular solution, so to find a particular solution, this is something extra that Kelly added in. The number of initial conditions must match the number of constants. So you're going to have sometimes more than one constant in your general solution. So you might have to have more than one initial condition to be able to find those values. And we're going to look at that a little bit in example 2. Okay, and lots of words here. So for the differential equation, xy prime minus 3y equals 0. So it is a differential equation because I have at least one derivative in there. But notice this one has both x and y. So a lot of them do. This one's just a little bit different than what we looked at in example 1. And I want to verify that this y equals c x cubed is a solution. And that is a general solution, right? I have a c in there. That's a general solution. And then I want to find the particular solution determined by this initial condition, y equals 2 when x equals negative 3. So first we're going to do the verify part. So we're going to first verify that, let's see, xy prime minus 3y equals 0. So the way I'm going to do that is I'm going to start with my my general solution, y equals c x to the third, start with my function, and we're going to take a first derivative. I don't need to take a second one for this. I only have a first derivative here. So y prime is going to be, this is power rule, so 3c x squared. All right, now I want to substitute in here and see if this works. So to verify, let's see, we're verifying xy prime minus 3y equals 0. I wouldn't have to really write this down again, but I want to make sure you understand what I'm doing. So x is just x. Y prime is going to be that thing I just found, 3cx squared. And then I have minus 3 times y. So y is going to be the cx cubed. And then I'm checking to see, does it equal 0? And it should equal 0, right? Where it says verify on this one, it's not saying like tell whether or not it is a solution. So here the x times my x squared gives me a 3cx cubed. Over here I have 3cx cubed. So it does work. So I verified it. And now I want to solve for c to find a particular solution. So now I'm going to find the particular solution. So my initial conditions, trying to get us used to this vocab. We've done this before, but they didn't call them initial conditions. Y equals 2, x equals negative 3. So that means in my original function, y equals cx cubed, I can put in numbers for y and for x. So my y is 2 and my x is negative 3. So let's see, negative 3 cubed would be a negative 27. I'm going to write it as negative 27c. So 2 divided by negative 27 would be equal to c. So that tells me what c is. So that means my particular solution would be y equals negative 2/27 x cubed. So this is my particular solution to that differential equation. And we proved it works over here for any value of c, so this particular solution is automatically going to work as well. All right, so let's go ahead and flip to the back. And we're looking at slope fields, which I know we spent some time with on Friday with that worksheet. Still need to scan those answers in for you. So slope fields are short slope segments. And they form a slope field. Field needs an L in it, or a directional field. And this problem, we need to fix this. It should be y prime equals x minus y. So hopefully looking at that, you're like, huh, something's wrong. This should be x minus y instead. So minus sign right here. And we want to do this only at 3 different points, -1, 1, 0, 1, and 1, 1. So the way I find that slope is I'm using my y prime or my dy dx. That's really my slope, right? So in order to find my slope at -1, 1, I would plug into that differential equation. Y prime equals x minus y. I can call it a differential equation because it's got at least one derivative in it. So my slope, remember this is my slope. That's my dy dx. My x is -1 minus my y is 1. So that's going to be a -2. So at -1, 1, I want to make a slope of -2. So here's -1, 1. So think about how a slope of -2 would have this angle to it. And then I just want to draw a little slope segment representing that. And I'm going to erase all that extra. So sometimes it helps to kind of draw in what the slope would look like and think about connecting that to some points. At 0, 1, let's see, I know my slope is going to equal, let's see, it's x minus y, so 0 minus 1, which is -1. So at 0, 1, I want to draw a -1 slope. So here's my 0, 1. A -1 slope would be like that. That would be like a -1 slope. So I want to draw that little direction right around that point. And then I'm going to erase off my extra again. At 1, 1, my slope would be 1 minus 1, which is just 0. I know that 0 slope is a horizontal line. So at 1, 1, I'm going to make a short little horizontal line. So last problem, we're going to look at matching some slope fields with differential equations. So on these, I would really recommend trying to find, like on this first one, I can find this whole column here where my slope is equal to 0. It's really hard with these segments that are angled to tell if you're looking at a 1 slope or a 1/2 slope or a 2 slope. They all look really close, but the 0 slopes are easy to identify. So this would be all the spots where x equals 0. It looks like my slope is equal to 0. Remember, my slope is my y prime. So when x is 0, my slope is 0. And then I want to see, does that work over here? So if I put a 0 in for x, I'd have y prime equals y. That's not going to work because here I would have y equals 2 or y equals 3. 0 plus 2 or 3 would be a 2 or a 3, and that's 0 all the way up, so it's not going to be that one. Over here, I have my y prime equals my x. That seems to make sense there, doesn't it? Because everywhere that my x was 0, my slope was also 0. So I'm going to match these two together. On the next one, do I have any 0 slope? Sometimes they're hard to find. Oh, it looks like they're right through the middle here. So I have a 0 slope at 1, -1. M equals 0 when I have a slope at 0, 0. I have a slope at -1, 1. So let's go through and let's check here. So it's not going to be this one. because my slope is not just equal to my y value, because I've identified the slope as 0 at all these places, but my y's are -1, 0, and 1. They aren't all 0. So let's check this over here. So if I do 1 plus -1, that's going to be a 0. If I do 0 plus 0, that's going to be a 0. What was the other one identified? -1 plus 1 gives me a 0. So these two are going to match. And then for my last one, y prime equals y. It's really hard to see on the copy that you have from the book. I had to scan it, but there are a bunch of like little tiny horizontal segments on here. So if you look at this example in the book, you're going to be able to see it better. I can barely see it on a couple of mine, but what this is showing me here is that when my y is 0, my slope is 0, or my y prime. So that's going to be this last one. That's going to be 3. So kind of look for the slopes that are 0 and try to use those. We could also think about so if this is a map of my derivative, those little slope segments for my derivative, I could also go through and I could think, well, if this is my derivative, what is my original y going to be? And so if I integrate this, the integral of x, when I integrate that, my antiderivative, maybe I should say it that way, is going to be x squared over 2 plus c. So if I think about the shape of x squared, and then I think about the shape of these graphs, of these slope fields, they do form that parabola. So that would be another way to kind of further that idea. So slope fields are really super cool. All right, this is it for our 6-1 notes. Just go ahead and email me questions if you have any, and I'll see you in class as soon as I can.